Okay, so let's start our discussion. So in the previous few sections of classical mechanics, we have discussed so many things like the Lagrangian mechanics, Lagrangian formulation, the superiority of Lagrangian formulation over the Newtonian, and discuss the various derivation of Lagrange's equation by D'Alembert's principle. Then we have proceed to some applications of the Lagrangian formulations. Now it is the time to discuss the Noether's theorem. Now, although the Noether's theorem is very important and it is new to you, but its application has already been done in the previous few sections. After describing what is Noether's theorem and also the proof of Noether's theorem, we will return to the application of this. Okay, when I will return to the application, then you simply recall what I mean to say, that the application was previously done. Okay, so without wasting any time, let us proceed to the statement of the Noether's theorem. So statement, what it says that every symmetry transformation is associated with some conserved quantity. Conserved quantity. Okay, now let us discuss point to point what is the actual meaning of the statement. Now at first you can simply ask what is symmetry transformation. Okay, so symmetry transformation is nothing but the transformation of the Lagrangian equation with respect to some quantity. It may be some physical quantity like time, position, etc., velocity, etc. Some physical quantity. When we transfer the Lagrangian of a system, or we can check the variation of Lagrangian of a system with respect to this physical quantity, and the Lagrangian remains invariant, that is the change will be zero, then we can simply call this as the symmetry transformation about this physical quantity we are considering. The physical quantity which we are considering, the Lagrangian is symmetrical with respect to this. Okay, so we have to prove, and the statement simply tells about the symmetrical transformation with respect to which physical quantity we consider the physical quantity will remain conserved. Okay, suppose the physical quantity we considering is S. S is a physical quantity. We are interested to discuss the Lagrangian transformation. Is the Lagrangian transformation symmetric with respect to S or not? So at the first point we have to consider that the Lagrangian is symmetrical with respect to this physical quantity to prove this statement. Now if the Lagrangian be symmetrical with respect to this physical quantity, then the change in Lagrangian with respect to this should be zero. That is, Lagrangian is invariant with respect to this physical quantity. We are going to use this property. Okay, so proof. Suppose we consider a family of transformation represented by Q, which is a function of time, and it is transferred to some coordinate Q, which is a function of S as well as T. Now the Lagrangian corresponding to this new physical coordinate can be represented simply by L as a function of Q, which is also a function of S and T, generalized velocity Q dot, which is generalized coordinate q, generalized velocity q dot, as well as time. The Lagrangian corresponding to these new types of physical coordinate is represented by this. Okay, here S should be real physical parameter. Now we are going to estimate the variation of Lagrangian with respect to this physical coordinate or physical quantity. Okay, so we have to apply the chain rule for this. At first, del L del Q del Q del S plus del L del Q dot del S plus del L del T del S. Now what can we conclude from this line is that this delta del S, delta T del S should be 0. Why? Because Q is a independent uh, function of S and T. What does it mean? S and T are independent to each other, and Q is a function of both S and T. So T does not depend on S and S does not depend on T. So the variation of one parameter with respect to the other should be 0. So this term should be 0 and this term will be eliminated, and this will result delta L delta Q del Q del S plus delta L delta Q dot del Q dot delta S. Now from the Euler-Lagrangian equation, what we have discovered that the Lagrangian equation can be represented as d dt of del L del Q dot minus del L del Q is 0 for conservative system. Now this can further be modified as del L del Q dot is equal some del L del Q, which we can replace here. This. So this term can be replaced by this d dt of del L del Q dot, and delta Q delta S remains same, plus what we can represent this delta L delta Q dot remains same. We can represent it like this delta Q delta S. So these two terms belongs to d dt of delta Q delta S dot uh, delta L delta Q dot. And from our assumption that the Lagrangian is independent to the physical coordinate physical quantity S, so that delta L delta S is 0, so this term should be 0. If this term should be 0, then this should also be 0. What does it imply? What does it imply? d dt of some physical quantity 0 means the physical quantity is conserved or constant. Okay, so from this we can conclude that delta L delta Q dot delta Q delta S is conserved, or we can consider another parameter H. So H is constant. Now again from the Lagrangian mechanics we know that delta L delta Q dot simply means P. So this can be represented as P delta Q delta S is H, which is conserved. For considering all the coordinates, the total quantity, that is sum over J is equal 1 to degrees of freedom F Pi delta Q I delta S J is equal H, which is conserved. So H is the physical parameter resulting out to be conserved for the symmetrical transformation about S. Okay. So what does the theorem states? It is very simple, that every symmetry transformation is associated with some conserved quantity. So we have considered that the Lagrangian is symmetric with respect to some physical parameter S, and this assumption or this statement gives out to the another physical quantity to remain conserved for the system, which we have called as H. Now if I give some example, then it will be better to understand for you. Likewise, we have already considered that if the Lagrangian be independent to that of time, which is also a physical quantity, then the total energy corresponding to the system remains constant or remains conserved. So the Lagrangian is symmetric with respect to time, and this statement gives out to the conserved quantity, that is energy. Likewise, if we consider the space symmetry, then this will gives out to the conservation of total linear momentum. As well as if we consider the rotation symmetry of the system, then it will result out to be conservation of angular momentum. So if we are going to discuss some example, then the first one we can say that space conservation or space symmetry. Space symmetry. So Lagrangian is independent of the position, that is delta R, delta L, delta R should be 0. For all the system of particles, then this okay. So this, now from Euler-Lagrangian equation, I is equal 1 to some n d dt of delta L one minute. This is delta. Okay. This is not the n. This is degrees of freedom. The number of equations corresponding to the Ri should be f degrees. The degrees of freedom. The number of equation of transformation corresponding to Ri gives out to the a number of degrees of freedom corresponding to the system. So I is equal 1 to f ddt of delta L delta Q I dot minus delta L delta Qy is 0. This is Euler-Lagrangian equation. Now if we consider for single case ddt of delta L delta Q, a single I we have considered first, then it will be better to understand the sum. So this is 0 for single I. Okay. Now this quantity is also 0 due to the space symmetry. So this term gets cancelled out. results into delta L delta Qi dot to remain conserved. As already stated, what is delta L delta Qi dot? P, the canonical momentum corresponding to the system. So Pi dot is conserved. If we apply this to the summation, then we will get sum over I Pi, sorry, Pi dot, not Pi dot. Pi dot is 0. So Pi is conserved. Sum over Pi is conserved. So by considering the space symmetry, that is the Lagrangian is symmetrical with respect to the space coordinate, we get out as the linear momentum to be conserved corresponding to the system. Likewise, if we consider the Lagrangian to be independent of time, that is Lagrangian does not depend upon time, q, it only depends on these two quantities, then we can consider the variation of Lagrangian with respect to time as delta L delta T is, or better to say, we can consider from Hamiltonian, or from this also we can say. Okay, let us see. From this what we can obtain, dl dt delta L delta Q Q dot plus delta L delta Q dot Q double dot, okay, plus 0. Now this is nothing but d dt of delta L delta Q dot, and this is Q dot, and this is delta L delta Q dot, this is d dt of Q dot. So d dt of delta L delta Q dot minus Q dot. So what we can obtain, dl dt minus d dt of delta L delta Q dot is 0, or we can say d dt of, this is p Q dot minus L, this is p Q dot minus L is 0, that is p Q dot minus L to be conserved. Now again, P means delta L delta Qy dot minus L is conserved. So delta L can be represented L of T minus V delta Qy dot minus L conserved, delta T delta Qy dot minus L is equal conserved. Why? Because del V del Qi dot is 0, and from our general Euler equation rule we know that the kinetic energy is quadratic of position, so this results nothing but 2t minus Lagrangian means T minus V, so T plus V conserved, that is T plus V is conserved, that is total energy is conserved. So by considering the Lagrangian to be independent of time, we get out the result as total energy corresponding to the system is conserved. So these are two applications of the Noether's theorem. Although the theorem is new to us, but the applications are not new to us. So this was all about today's discussion. Thanks for watching.